Swayam Prabha. Digital India. Educated India.
Welcome back to this lecture series on cyber physical systems. If you remember, in the last lecture we were talking about bus of attacks on CAN buses, right? And we established that what can be the objective of the attack, and we will now try to discuss the algorithm which is to be implemented by this malicious node and see that how that attack can happen in real life. So we are trying to show that, well, let's say this is one attacker ECU, okay, and it's going to push in some attack message on the bus, and let's say this is a victim ECU whom this attacker is targeting, and this victim ECU is generating periodic messages which are valid real messages. Okay. Now what can happen is, let's say these attack messages and these periodic messages are having the same ID. It's precisely that is what the attacker is targeting. It is targeting to replace these periodic messages of the victim ECU with its own messages. So this can be done in such a way that these due to the attack message injection there will be transmission errors. Now there is a problem here. Let's understand that it's not really easy also. The attacker will need to identify exactly at what time the victim's values are coming. So let's say it's a timeline and the victim is sending these messages periodically with a period of, let's say, 20 milliseconds. So this is a periodic data stream and there may be an offset, right? So I mean, let's say the first value started with a period. I mean, of course, the first value may have a phase like phi. So let's say every kth message, the transmission time is this phi plus k times 20, right? The issue is this phi is unknown to the attacker. So what is important is the attacker needs to first synchronize with this victim ECU. There are techniques for doing that. We are not discussing that here. So once the attacker has synchronized with this victim ECU, it should be able to send messages exactly at those time instants. Now once it is able to send messages exactly at those time instants, so you have two messages coming, right, at the same time with the same content, the attacker will force a transmission error. Okay. Now like we said that with multiple such transmission errors, this victim ECU's transmission error counts will increase and this will go to the bus off mode, right. So that's what the attacker is targeting, and for the time being, for an interval up to which, so let's say here things were fine and here an attack was launched, and at this point this ECU goes to bus off mode and this is the bus off interval after which this ECU is back online. Okay. So inside this bus off interval, the attacker is mimicking messages of this victim ECU with malicious messages. So this entire thing can start happening again, right? Again there will be an attack window and again there will be a bus off period, etc., etc., right. So if the attacker is smartly able to increase the bus off period and do this attack very often, there may be issues with the system. Of course, modern day CAN systems have learned how to bypass this kind of vulnerabilities, and they can prevent such attacks, but well, some issues still remain. So that's why this attack class is really important. So let's first understand this issue of how the attacker will force the victim to increase its transmission error count. So let's say this victim is transmitting its data stream and there is this adversary who is transmitting the data stream, and here is the CAN bus. Okay, the bus is idle here. What the victim is trying to do is he is trying to mimic the adversary's transmission data stream, and the first task of the victim definitely is that he will have to synchronize with this. First task for the adversary is that he have to synchronize with the victim's transmission timings. Okay, and then there will be a time when it is sure that it has got itself fully synchronized, and when at that time when the victim is transmitting a message, then this adversary will start transmitting a sequence of zeros. Okay. So, basically this is the point we are talking about, that when one arbitration phase is beginning, and at this point this the adversary is transmitting a sequence of zeros. The idea is that, well, it has to win the arbitration. Okay. So, the adversary is essentially forcing the victim to lose out the arbitration by transmitting a lower priority identifier which is having more zeros, and due to this the victim will eventually lose its arbitration, and that is why its TEC count will go to a +8, because this is not really a fair win, right, because they are trying to go start with two IDs where the adversary has tried to kind of assume the victim's ID, but with more number of zeros here. Okay. So, it will lose the arbitration, the victim will lose the arbitration, and after that what will happen is fine, whatever the adversary is sending, those values will be going, right. So, let us again understand the process. Initially the attacker will synchronize with the victim, and then there will be the original arbitration phase with every other node who wants to participate. What this adversary is doing is, he is using the same ID as the victim, and using that idea the victim will be winning, let us say, the arbitration at some stage with respect to some other lower priority messages by other issues, and the adversary is also winning that arbitration stage. Let us understand this, because this is not how the original CAN system is designed, right, because in the original CAN system a designer who wants his system to work, he will never have same ID for different messages in the system coming from different ECUs like that. But this is the adversarial scenario, right. So, the adversary who is sitting in some ECU will actually force the situation, or who is sitting in a newly attached malicious ECU coming from a rogue service center, stuff like that, or due to some code download which should not have happened, he is trying to send messages with exactly the same ID as the victim, right. So, due to this, what happens is, whenever the victim wins arbitration with respect to other competing messages, the adversary is also winning the arbitration. So, after this arbitration win, what they are doing is, whatever message the victim is sending, the CAN on the CAN, the adversary will send a stream of zeros. Now, let us understand that it is not that the CAN bus is going to check for arbitration at a specific phase and then it will transmit message. It is a simple two-way connection, right. So, it is always in AND mode. The arbitration happens right at the physical layer itself, there is no software logic. So, even the post arbitration phase, when there are two actual winners, which should not have been the case, even when the payload transmission is happening, the arbitration physics is still there, right. So, due to this arbitration physics of the bus, for the real payload transmission, even in that phase, due to the adversary sending a stream of zeros, it will eventually win, and the victim will receive a transmission error. And due to this transmission error, its error flag will, the transmission error count will go by a +8, right. Because here the victim can see that it was transmitting a 1, but the adversary transmitted a 0, and that is why this bit error happened here, right. So, let us understand the feasibility of this attack. The attack message will have the same ID as the target, and the content of the message which is inside the attack message will have at least one bit position in which it is dominant, whereas the victim's message is recessive. So, let us understand that what I am repeating maybe third time is, this is also an arbitration, but happening in the place where only the payload was supposed to be there, that is the content was supposed to be there. The original arbitration has already happened, and unfortunately due to this adversary is present, there are two winners here with respect to the other messages. Okay. Now, in the payload part, the contents are almost same, but there is at least one bit position where the adversary is dominant, right. So, this is what the adversary is aiming at, but what is important is that the adversary needs to synchronize its transmission time with that of the victim. That means, in order for this thing to happen, this is not very trivial. We are just speaking at a model and slide level, but let us understand this is also this requires significant hardware expertise and significant insight of the real time system when the packets are scheduled, how to push in a higher priority using scheduling tricks like higher and lower priority. It is possible for the adversary to actually synchronize with the victim at some specific points and attain this thing, that it is sending values exactly at the point where the victim is also sending. Okay, right? So what I am trying to say is this needs to be done, and it is difficult, but it can be done. The adversary can synchronize its transmissions with that of the victim, and the method at a high level is that it will kind of monitor the preceding messages and try to figure out when exactly it should be injecting its attack payload. So now let us go deeper into this situation. We have already said that there will be a transmission error count, right? But that is not the end of the story. The story is much more complex. So this is what we are talking about, that at the length of this DLC there is this bit error. The transmission error count of the victim is going increasing by 8, right? So TEC count increases by a +8. By the way, this attack is kind of detailed in this paper which was published in 2016 CCS. So the TEC count goes +8 here for the victim, but is that all? No. When this happens by the CAN protocol, what happens is the victim will kind of emit an active flag, the error active flag, which is a sequence of all zeros. Okay, and now due to this, what will happen is that the adversary, if it is doing any transmission, now this will be ANDed with this sequence of zeros, and due to that this transmission error, it will also have an error flag, right, because now it is getting ANDed with the zeros that are here, right. So what will happen is the adversary will now have a transmission error. So the adversary's transmission error count will increase by a +8, right. So that is fine. There will be a +8 here, and the adversary will also have a +8 here, but let us understand that they are not happening together. This is happening afterwards for the adversary, because this is a reaction to the error active flag from the victim when this sequence of zeros get ANDed with some 1 that the adversary is transmitting. Okay. So at this point what will happen is there will be an 11 recessive bits transmitted, the error frame as per the CAN protocol, and then the interframe space will be maintained, and then again the transmission cycle will increase. And let us say that the malicious node will it has its software, right, and it will just repeat this process. So while repeating this process, the victim's transmission count will again increase and the adversary's transmission count will again increase. So both of them are having a +8 increase, but for the victim it's happening earlier, and for the adversary it's happening later on. Now this would mean for both of them at some point they will reach 128, right, because see 128 is of course divisible by 8. So both of them will reach 128, and then again when the attack will repeat, the transmission count for the victim will go from 128 to a +8, that is 136. Now this is the important phase of the attack. This is phase 2 of the attack. So this is all the phase 1 in which both of them start doing +8 increase in TEC, and then we have a time when one of them is sitting at 128 and the other has also received 128, and the victim again goes to a +8. But now this is phase 2 of the attack, when what happens is this moves from 128 to 136. Now this is important. If you remember the original automaton of this protocol, we said that when this is beyond 127 beyond 128, right, so that's like it is moving from the error active to the error passive mode. So here as you can see that when this goes from 128 to 136, victim is following that original automaton and it is moving from an error active phase to a error passive phase. Now what is the difference that is coming out of this? The difference is when it was in error active state, due to each error it was sending an active flag which was a sequence of zeros here, right. But now while it is in the passive place, it will send a passive error flag, which is not such a sequence of zeros, and it does not dominate the adversary's any future message. So, due to that, I do not have any sequence of zeros coming, this is a passive flag. So, whatever transmission the adversary is doing now will be fine. Okay? And since that is fine, there will be no more +8 increase in the transmission error count of the adversary, rather it will be successful, and due to that the transmission error count will decrease by 1, right. So, at this point what will happen is this stays in 136 and this stays in 127. Okay. And after this there will be an 11 recessive bits here, and there will be 3 recessive bits due to the interframe space, right. And then what will happen is, well, for each successful transmission, because although I am in error passive mode, but still I can do transmissions, there will be decrements happening, right. So, there will be a decrement here in the victim to 135, right. Now, let us understand again, but this behavior will now continue. Now, again so this is happening because let us say here the adversary is not doing anything, okay. But and also what is important is to understand is this thing, that well, at this point in the error passive phase, what happens is that, well, you did something, you highlighted the error passive flag, but after that you will also try to do a retransmission of your original message. Okay. So, when you are trying to do a retransmission of your original message, which you failed initially, that will go through successfully. So, that is why there will be this a subtraction coming from 136 to 135. So, let us understand again. I hope this process was clear, that for everybody it was increasing, but now in this case, when it went for 128 to 136, the difference was, instead of an error active, the error passive flag came. Due to that, for the adversary there was no kind of increase of a +8, because it could successfully transmit. So, it actually had a decrease to 127, but then the victim went to the retransmission mode, and that was also successful, and it decreased to a 135, right. But that does not clear the problem, right. But now again, when every time there is a message collision created by the adversary, we will have this as +8, and we will have here a -1, and then there will be a retransmission, due to which there will be a -1 here. So, in effect what is happening is, every transmission the victim is having an effective +7 and the adversary is having an effective -1, right. So, in this phase 2, when the victim is error passive mode, so let us understand again, when I was in the phase 1, both of our TECs were increasing, with the only difference that for the victim the TEC was increasing in the previous cycle. When I come to phase 2, what is happening is, both for the victim and the adversary, I have I mean the victim will, since it was having these increments happening earlier than the adversary, at this point it will get inside the error passive mode, and due to that the flag will change from active to passive, and due to that the adversary won't get any transmission error increase, in fact it will be a decrease, and for the victim it will be a net increase of +7 with every collision, and this will keep on repeating in every round with a effective +7, right, and an effective -1 here, and this will keep on happening until and unless this guy goes to beyond 25, and that is when it's stuck out of the bus, right. So, it is in a bus of state for some period, and that is when the adversary who is sending messages with the same ID, those messages will keep on going only, and it can create instabilities, it can create unsafe situations with plants, right. So, this is how in the false data injection situation, the attacker destroys the integrity of the legitimate data, and the attacker first sends the node to a bus of state like we discussed, and then the attacker takes the victim's role and it will inject false data into the bus using the same ID, and that can destabilize closed loop dynamics of automotive control systems. So, that is a classical example how CAN buses vulnerabilities can be exploited, but like I said that there are countermeasures that have come into also, and CAN buses are nowadays I mean there are CAN FD, CAN with flexible data rate, where doing this synchronization may be difficult, and all these issues also come in. Okay. Now, this is a small setup using which you can actually do such a attack injection. So, let us say you have this Infineon board which is an ECU, and you are attaching a CAN controller and a CAN bus to that, and let us say there is you are running a controller in this board, and that controller is attached to a plant, and that plant is kind of running in this hardware in the loop simulator. It is a real time simulator where you are actually simulating the plant model in real time, and this Infineon Oryx TC397 board is where the CAN controller is running, and CAN traffic generator is also implemented. So, that is another code which is creating other messages mimicking other ECUs, and this is one ECU with some controller for the plant. And let us say you implement an attacker in another node which is an Arduino with a CAN shield. So, that is a CAN. If you can actually mimic such CAN nodes by using simple cheap Arduino boards and attaching CAN shields with them, right. The CAN shield is nothing but it has a CAN controller and transceiver, and it will emulate the attacker, right. Also, for measurement purposes, you can actually use a Cavaser CAN King monitor to the CAN bus. So, using such a monitor, you can actually attach this monitor to the CAN bus, and you can actually see what are the CAN messages. You can see that CAN message stream in a PC, right. So, using this setup, you can actually program and write the controller, program this controller using Oryx Development Studio, download it on the Infineon board. So, in a normal situation, the using this CAN bus from the board to the hill, you are sending messages for the plant, and the plant is running on this hill system, the hardware in the loop system. Now, you can attach, like I said, the other attacker ECU you can attach to the CAN bus, and you can also have some CAN traffic generated which mimics other ECUs, right. And when the attack happens, you can see, you can monitor that what really goes on. So, let us say this is your control input, and this is your system state. We are having a simple trajectory tracking control system, and eventually it stabilizes. As you see that both the control input and the system state are stabilizing here. But let us say you did such a bus of attack, and for a period you have taken this the ECU of the system, okay, and so from here there is no control input available right here, okay, and then because the attacker has assumed the identity of the ECU, and you can see that the system state is coming down. It was supposed to be somewhere around this reference, but it has come down. So, that is how we can actually see that, well, due to such false data injection, what can happen to a plant. So, we can actually study that. So, that is about some examples of how CPS attacks can really happen. With this, we will end this lecture. Thanks for your attention.